Okay, cool. So if there's no questions, let's go on with today's first thing, the notice and wonder. So, before notice and wonder, let's do a recap. So, the recap, what we did last week is we talked a little bit more about the unit circle, and I talked a little bit about how the unit circle moves, or how not how it moves, how we create angles inside the unit circle. And I use mostly this kind of visual to explain that. So you usually start on your initial side, and it's always on the positive x-axis. The terminal side is that ray, the second ray, that's kind of like rotates about its vertex right here in the picture and creates an angle. So you rotate it this way to create your positive angles. And this direction is called counterclockwise. But you can even move backwards. And when you move backwards, clockwise style, right, like this way, that makes negative angles. So moving backwards makes negative angles. And last week, we talked about radians, right? We kind of talked about how to convert from degrees and radians. So now we kind of know what these numbers in red represents. And we also know what these numbers in blue represent because these are just degree measures and you're counting as you rotate counterclockwise. So today, we're going to be focusing on what are these coordinate points and where do they come from? So that's going to be today's focus. And then let me know if anyone has questions about that little recap there about where we left off. And I think there's a second part. No second part. So let me know if anyone has any questions about this recap here before we jump into our notice and wonder about a windmill.
So it's like a graph, but on a circle.
That's right. It's like a graph and on a circle. You could imagine this is like a circle on the origin. Like here you have 0, 0. Notice how right here it's 1, 0. Over here it's 0, 1. So this is literally on the coordinate plane. That's right. It is a graph and it is a circle. And you can create angles inside here. That's right. Love that. Any other clarifying questions or anything about our little recap here? All right. There's no last burning clarifying questions. Let's move on to today's notice and wonder. And this notice and wonder is kind of going to ask you what kind of questions can we be asked about the motion of this windmill? So this is a windmill. I want you to think about what kind of questions can you be asked about it. Maybe you could think about like how can this relate to the unit circle? I'm going to go ahead and stick our Padlet in the chat. If you're with me, I see Francisco there with me on this slide. Again, do make sure you open up your own copy. If you haven't yet, it's on Google Classroom. But we are period 1, so it would be right down here. I'm going to go ahead and put this into the chat. This is going to be our first participation of the day. And let me open it up with you. We'll have about a minute on this, and it is going to be column number. Let's take a look at where we left off. Let's see. We are on column number 6. Notice and wonder. What kind of questions can you be asked about the motion of this windmill? I see a lot of amazing folks already starting to type up. Awesome. Make sure y'all put your name or initial. And let's start to hypothesize. What kind of questions would you be asked? I'm going to put the directions in the chat once more. There you go. Directions in the chat. Let's take about 1 minute, then we'll come back and take a look at what y'all think. Hi everyone, I see that we're still writing, so I'm going to give a few more seconds. I see some amazing like wonderings and possible questions you might be asked about this windmill. All right, welcome back everyone. Go ahead and finish your thought if you haven't just yet. So here we have a windmill, and I saw a bunch of great questions coming up, right? I saw a lot of you wondering, like, what does this point P mean? A lot of you were talking about, like, does it rotate counterclockwise or clockwise? Which is a very good question, because remember, if we're talking about the unit circle, if we're going counterclockwise, we know we have positive angles. Whereas if you're going clockwise, the opposite direction, we're going to be dealing with negative angles. So that's an amazing question. There were other questions coming up. Yeah, so which side would it rotate? How will the energy be affected? Ooh, we're talking about energy. I wonder we'll talk about that. Could be affected when it rotates either left or right. That's true because windmills are used sometimes to reduce energy. I love that. Wondering what that letter P means. Oh yeah, how fast is the wind? How fast is the windmill going to rotate, right? I wonder if it'll be asked about the circle the windmill makes as it spins and what the circle has to do with the windmill itself, right? So are we talking about this unit circle, or are we just talking about general circle? What's the difference between left and right rotation? Oh yeah, and the difference there would be negative or positive angles. So if it's going counterclockwise, or you could call that as, if it's going counterclockwise, we're talking about it moving towards the left, that would be positive angles. Going clockwise would be moving to the right, I think. If I'm understanding that right, and that would be a negative angle. So that's an amazing, good question. Which way will it spin? Will it spin faster if it spins to the left or the right? How fast will it rotate? I wonder where the point is, if it will change, stay the same. Wow, these are so great. And I don't have time to read all of them, but let me see if there's any others that are standing out to me as different. Um, if the motion affects the radius, so I'm seeing that we're bringing in like some of the words we've been talking about. How is the radius going to kind of affect this? Okay, so there's a question. I wonder if the motion of this windmill might be related to the way the unit circle can be solved, like degrees and rotation. Ooh, so that's like a possible question you could be asked. I like that. We got that wondering of clockwise or not. And let's see if there's anything different. Yeah, we're wondering if we're going to use the circle to figure something out. I like this one too. Will it be more than 360 degrees? So are we going to be doing over 360 degrees? I mean, it depends if the windmill rotates more than once around, then you're going to be talking about more than 360 degrees. And then miles per hour it's going. And I wonder what would be I mean, now that's bringing me up a wonder, like what would be the appropriate units of measurement when it comes to a windmill? Would it be miles per hour? Would it be feet per minute? I'm thinking about the units as well. I love that question. All right, y'all. Thank you so much for this participation. That's kind of we did this notice and wonder so that you could probably kind of try to make some connections with what we're learning right now and why perhaps we would want to know what the coordinates on the unit circle mean. That's going to lead us into today. So I'm going to go back to our slides. Thank you so much, everyone. And I am on slide number 6. The coordinates of the unit circle is today's focus. The learning target is I can explain where the coordinates from the unit circle come from to the best that we can. So we're going to try to kind of just understand like where are those numbers coming from, and we'll investigate this together. Yeah, so don't worry, group works will be coming up. So I definitely value group work. I think that's where a lot of our learning happens. So don't worry, stay tuned for group work. I'm looking forward to that. Okay, cool. So let's go ahead and keep this learning target in mind, and then let's move on to slide number 7. So y'all, today we're going to be focusing on what do I first off mean by coordinates of the unit circle? I'm talking about those things in parentheses, like the x comma y. These are the coordinates of your unit circle. The coordinates on the unit circle basically represent specific locations, right, on the circumference of your circle. Maybe if you're thinking about the windmill, it could represent where P is. You know how some of you are like, what is P? Maybe what if you're tracking where that point P is, and over time you want to know like what specific location is it at? Like what are its coordinates over time? That could be a possible connection to the windmill. And then we're going to talk about where these coordinates are coming from. And to make life easier, y'all, I'm actually going to just focus on the first, what we call this is called the first quadrant. Let me circle this. This is the first quadrant. We're going to focus on the first quadrant. I don't know if y'all made a little bit or noticed this, but when you're looking at the coordinates, don't you notice that they're kind of repeating a bit? Except the signs are probably changing. Like I see root 3/2 right here. I see it once more here. I see it once more here. Except, so yeah, so this is the same. I see 1/2 over here. I see 1/2 here, yet it's negative. I see the root 2/2 and I see it again over here. So notice how like the numbers are kind of repeating, but perhaps their signs are changing. So the strategy here will be, let's just figure out how we get the coordinates for the first quadrant, and then we could figure out where these other coordinates are coming from in the other quadrants. Let me know if anyone has questions about how we're going to kind of investigate this. So we're just going to focus on the first quadrant, and then we're going to see how we get the rest of the coordinates on the unit circle. And again, feel free if you're following along, take a little note like, hey, we're just focusing on the first quadrant. The rest of them should kind of come nicely once we know how the first quadrant is being created. Yeah. All right, I'm going to go ahead and clear this up. And let's go on to the next slide. So what do the coordinates mean? It could mean something about position of the windmill. We don't know yet, but how are the coordinates being made? How do we know these coordinates are there? Like, how do we know it's root 3/2? How do we know it's 1/2? Like, where are these coming from? I'm going to go ahead and remind you of this tool that we looked at, I think on Thursday. So if you remember this tool basically, see this A right here that's moving, this is representing degree measure. This right here is a unit circle, but you want to notice it doesn't have any radians on it. It just has degrees on it. And as I increase my A, as I use this tool and slide my A, notice that you all noticed actually last time that this was creating a right triangle. So if we're using our proper vocabulary, we start right here. This is the initial side on the positive x-axis. And when I start to lift it, that second side right here, where my mouse is at, the second side, this is your terminal side. And let me grab my tool. And I am rotating this way, so it's a positive angle. This was called terminal side. Terminal side. And then at the bottom, we had the initial side. That just stays flat. You have to just imagine there's like a red thing here. That's your initial side. And then basically what's different here is this. If you drop a straight line down, a perpendicular line basically, what you can do is you're creating right triangles inside the unit circle. So this is a right angle right here. And what we have is a triangle. We're going to be using the triangles inside this unit circle to figure out what the coordinate points are. So that's what we're going to be doing next. And again, a lot of you noticed that there were triangles being formed in here, and y'all had other notices that's going to be super relevant to this. Let me just go ahead and clear my screen now. And I also want you to notice that if I'm on this tool, you could click on the point itself and it gives you coordinates in decimal form. These coordinates in decimal form are equivalent to the coordinates you would see on the unit circle back if you look on our slide, except the coordinates on the unit circle you see are in fractional form, see? So if you were to use the tool and you click on it, it's going to give you the decimal form of those coordinates, which right here are in fraction form. Let me know if anyone has any clarifying questions about that. But that's how, like, you know, to relate what's happening in the tool. And again, y'all, the tool is on slide number 8. So if you want to continue to explore and play around with the tool, feel free to. But we did take a look at this on Thursday of last week. So we're going to be using those triangles, those right triangles that we saw in this tool, and we're going to try to create the coordinate points in the first quadrant. We're trying to figure out where they're coming from. So let us go ahead and transition now to slide 9. Another thing that you should pay attention to or notice, someone mentioned this in the Padlet. They mentioned that the hypotenuses of all the right triangles in the unit circle are length 1. So what I mean, so let's say I want to create a right triangle right here. Y'all see this purple one? This purple right triangle right here has a measurement of 30 degrees. So that angle down here is 30 degrees, which is equivalent to pi over 6 radians, right? So that is my first triangle that I made. And this length, let me do it in a different color. The length of its hypotenuse, that's right here, is going to be 1. Why? Because this is a unit circle. The radius, or any line from the center to the circumference of the circle, or from here to here, is 1. From here to here, that's also 1. Here to here, all around the circle, right? Anywhere from the center to the radius, all of these line segments have length 1, because this is a unit circle. It has a radius of length 1. So that means the hypotenuses of all of my right triangles are going to be length 1. That's going to be nice because it's going to make our calculations easier. So let me just erase these lines. So this is my first triangle right here. It's a 30-degree angle triangle that I made. Let's look at what other ones I could build. I could see next off right here, it's 45 degrees or pi over 4 radians. Let's create that second one. That's how that one would look like. Then up here, I see there's 60 degrees, which is equivalent to pi over 3. Let's just see what that one looks like. We're gonna today break down how these 3 triangles, creating those, are gonna help us determine what these coordinate points are. So that's our goal today. And I'm hoping these visuals, like, it would sound like kind of weird if I just said this without the visual. So definitely pay attention to the visual and how we're explaining this. So let me just pause, see if we have questions right now about what I just said or anything about how we're going to get started here. Okay. And again, if you have questions, feel free, even if it's like I went on this slide, feel free to continue to ask your questions. So this is what we're going to look at, everybody. So I don't know if you noticed that we're looking at a 30-degree, 45-degree, 60-degree angle. Those actually have a very strong correlation to special right triangles that y'all learned in geometry, everyone, actually. We're going on to slide 10. Da-dun. I don't know if y'all remember these. Special right triangles to know. Do y'all remember 30, 60, 90 triangle and 45, 45, 90? If not, it's okay. But these are special right triangles. These special right triangles help us create some of the essential points on the unit circle. And again, we're just going to be focusing on the first quadrant, but you're going to see later on how we're able to get all the coordinate points. So this is from geometry, and we're going to be focused on this. Why? Well, remember when I was drawing those triangles in the unit circle right now? One of them was a 45-degree angle triangle. One of them was a 30-degree. One of them was a 60. So we're kind of taking care of those three triangles that we saw by investigating these special right triangles. So that's awesome. So it's okay if you don't remember these because we're going to work through this together. And I'm pausing to make sure you all get a chance to write your little notes if you have them there on your slide. Again, you want to make notes on your own copy of the slide. Okay, let's go on. Is this the math slide? Slide number 11? Yes. Okay, so we're going to be doing this first triangle. We're going to do the special right triangle, 30, 60, 90-degree triangle. We're going to need to use two things. We're going to need to use, well, the fact that first off, on the unit circle, the hypotenuse of all right triangles is 1. That's one fact. Another thing we're going to be using is SOHCAHTOA, right? From geometry, we're going to be using SOHCAHTOA to help us out. And once we're done with SOHCAHTOA, so I'm not going to start that yet. Once we're done with SOHCAHTOA, the next thing we're going to need is the Pythagorean theorem. Some of you mentioned that theorem before. That's just going to go on this side. So before we use it, I'm just typing it there so you know what we're going to use. So we're using SOHCAHTOA, we're using Pythagorean theorem, and we're using the fact that the radius of all the right triangles in the unit circle have length 1. So that's what we're our tools here. And please try your best to pay attention. We're going to have a Padlet check here. This is going to have some math here. So feel free to, in the moment, go on a piece of paper and start copying down if it helps you. Or, pre-prepared to ask some questions, all of that. All right, y'all. So the first thing I'm gonna start with is with SOHCAHTOA. And I'm gonna focus on the 30-degree angle. So I'm gonna focus on this guy right here, 30-degree angle. The next thing I'm gonna do is I'm gonna label my sides to apply SOHCAHTOA. I'm gonna be specifically right now focused on sine. So that's what I'm gonna do first. So I'm gonna do sine. I know that's opposite over hypotenuse. So let's label the sides. So the side opposite of my 30-degree angle, I'm focused on the 30-degree angle. We're going to call this opposite. The longest angle right here is length 1, and that's always the opposite of the right angle. We're just going to call this hypotenuse. That's always opposite of your right angle. And the remaining side is called adjacent. That's an A. Yeah. The remaining side is called adjacent. Now let me see, I saw something in the chat. Awesome, yes, Francisco, you put opposite over hypotenuse. That is your sign, perfect. We're gonna be using that right now. Amazing. Okay, so we're gonna find right now the sine of 30 degrees. We're just gonna build up some knowledge here, see what we can create, and see if we can make any connection with the coordinates on the unit circle. So here we go. So sine of 30 degrees we know is opposite over hypotenuse. Step 1. Sine of 30 degrees is equal to opposite over hypotenuse. Notice how instead of me putting hype, I just put 1. That's because our hypotenuse is equal to 1, because this right triangle is on the unit circle. So that's super, super vital right there. Well, everyone, anything divided by 1 is just a number itself. So that means this right here is going to become sine of 30 equals op, or just opposite. Okay, so we have that the opposite side is going to be equal to whatever sine of 30 is. Well, what is sine of 30? Now, in geometry class, I believe y'all had like a little chart. Didn't y'all have like a little number chart y'all would use? Right? Let's see what's in the chat. Oh, okay. How did you know it was 1/2 already, Francisco? That's, yeah, how'd you know? It is 1/2. Oh, okay. I did it for, okay. Look at this prior knowledge. You did it for asynchronous number 7. That's amazing. And for the rest of us, let's say you don't remember that, or let's say you still got to do asynchronous number 7. Do not fret, because we have handy dandy calculator. So if you haven't, yeah, if you have if you have okay, your phone, right? It looks like this, and it doesn't have like that much tools. It doesn't have sine or cosine. And then it says the guy in Khan Academy showed you. That's awesome. I'm going to rotate my phone, and it gives me more tools. So either you have a calculator or use your phone for this, everyone. And what I'm going to do is my phone right now, if you look, is set up on Bradian mode, I believe. It says rad right here. I need to first make sure it's on degree mode, because we're talking about 30 degrees. So that's step 1. Make sure your calculator is correct. So I just clicked degrees, so perfect. So I'm going to do sine, or I think I have to do 30, and then I click sine. When I did that, I did 30, and then I hit sine. It got me 0.5. So Francisco, yes, that Khan Academy guy was correct. And if you didn't know that, it's on our phone. We could just do sine of 30 degrees. You should get 0.5, which is equivalent to 1/2. That is correct. Let me know if anyone needs me to re-explain that, but we got our phones. You even have a Google calculator. You could use it online. But that is correct. Sine of 30 is 1/2. So that's how we got this. Sine of 30 is 1/2. Phone, or if you did asynchronous number 7, as Francisco said, you probably have that background knowledge of sine of 30 is 1/2 indeed. Okay, awesome. So we got that the opposite side has a length of 1/2. Hey, do you remember seeing 1/2 on that unit circle? Where is that coming from? Or how are we creating those coordinate points? Maybe that's going to get some of us to think about that. So we know that this opposite side has length of 1/2. So I'm going to go ahead and label that as 1/2, as you see popping up down here. Okay, let's continue to solve for the rest of this triangle. So there are 2 different, you could have actually, hey, for extra credit, if you want to figure this out, you can use SOHCAHTOA to find the remaining side. I'm going to actually use Pythagorean theorem right now. So there's 2 different ways to kind of solve the triangle. I'm going to try to find the adjacent side next. I'm going to personally use Pythagorean theorem, but for extra credit, if you want to, you could turn it in or on Remind, whatever. It could replace an asynchronous assignment. But if you want to show us how to do it with SOHCAHTOA, how to find the adjacent side, feel free to do so. But I'm going to use Pythagorean. All right, let's do this. I'm going to delete that because I know I wrote Pythagorean up there. There we go. Pythagorean theorem is what I'm going to do next. So y'all remember Pythagorean theorem? I think so. Some of you mentioned it on the Padlet. It's a squared plus b squared equals c squared. A squared, A and B are basically the legs or lengths on your triangle. And your C is always the hypotenuse. So basically, you could say adjacent is your A, and my opposite is my B, and my C is the hypotenuse, which is just 1. So you could think of this as A, B, C. If you'd like to, I'm going to go ahead and just plug in next. My next step is I'm going to plug in. So my A is basically the adjacent side. My B, I plugged in as 1/2 because the opposite side was 1/2. And C, which is always hypotenuse, I plugged in as 1. So I'm using Pythagorean theorem right now to find out what A is. A is the adjacent side. So I'm just re-emphasizing what I'm doing right now. And again, we're going to have a Padlet check right after this to process our understanding on this. Again, this requires some focus, have some coffee, have something ready to help you. Okay. And what I'm also going to do is, for those who need me to label the side, I will do so. So I'm saying this is A, I'm saying this is B, and I'm saying this is C. So that's if you need me to label the sides for the Pythagorean theorem. Okay, now let's go ahead and kind of simplify this. So 1 squared, that means 1 times 1. This is 1/2 squared. That means 1/2 times 1/2. If we do that correctly, right, you should get that a squared plus 1/4 is equal to 1. So 1 times 1 is 1. 1/2 times 1/2 is actually 1/4. I could even show you what I mean, show you that side work. So I'll go over here. 1/2 times 1/2 is equal to 1/4. Because 1 times 1 is 1, 2 times 2 is 4. So that's how we get 1/4 right here. And then 1 squared is just 1 times 1. A lot of people get confused thinking this is 1 times 2. Nope, this means 1 times 1. So this is what we have here from the Pythagorean theorem. And again, our goal is I'm trying to figure out what the length of this adjacent side is. All right. Now, to figure out what that adjacent side is, I'm trying to figure out what this A is. A for me is the adjacent side. So what I'm going to do is try to solve for A. Let me try to ask you all, what should I do next here if I want to solve for A? Let's see what ideas y'all have. Anyone in the chat, or you can unmute. What are some ideas we can do? Okay, we got divide both sides.
You could, oh, never mind. I was gonna say divide both sides.
Divide both sides as well. What would we divide? Oh, by 1/4? Okay. So I'm interested in the division because usually when you do something to one side, it's usually the opposite. Okay, so we have Henry. I wonder if, okay, like the other one, the right divided by 4. I see that there is a division by 4 right here, right? But then I want to hear, so Henry, you said subtract. Why do you say subtract? Because we have a different idea here. Either we divide or we're subtracting. Two different things are happening. And then perhaps the subtraction is coming because there's a plus right here. But let's see if you'd like to share, Henry. Why do you think it'd be subtraction? And feel free to either chat or mute, or you don't have to either. And Francisco, you said, oh, do the opposite, right, Henry? You follow PEMDAS, but backwards. Yeah. So I'm gonna have to agree with Henry too. So if we were to have divided by 4, I want to entertain that. I do want to make sure we talk about why it wouldn't be divide by 4. So if we were to divide by 4, you have to divide your whole left side by 4. That means you would even have to divide the a squared by 4. And then you would have to divide this by 4. Not only that, but basically this setup will not cancel out this 1/4. It would not get rid of it. In fact, you get 1/4 divided by 4. And that's going to give you, if you do 1/4 divided by 4, yeah, that's okay. Liking Sokotoa better, don't worry. We got this. That would give you, I believe, 1/16 if you were to do this division. So it wouldn't get rid of it. So that's why we definitely want to discuss the why. Yes, you want to go opposite. So I'm going to entertain what Henry said to do. Let's try it. So let's not divide. Let's try to subtract. And I showed you the why. The division actually would complicate things. Oh, I think I wrote this down actually. Hold on. Subtract both sides by 1/4. When you subtract both sides by 1/4, positive 1/4 minus 1/4 goes away. See that? That's how that completely turns to 0. And then Janet already said that 1 minus 1/4 right here is 3/4. And if you didn't know that, you could have, converted it to a decimal. But what you're left over with is a squared equals 1 minus 1/4 right here. And that is going to indeed be a squared equals 3/4. Just as Janet says. Does anyone have any questions as to why it's 3/4? Let us know, and I'm happy to answer it. It could be private message, or it could be toward everyone, whatever. We're all learning.
Can you explain? Yeah, because I'm
Yes. So 1 minus 1/4. So I'm going to go ahead and explain why 1 minus 1/4 gives us 3/4. This 4 is kind of cut off, but how does this go to this? Okay, so what we have to do is I'm going to do my work up here. Let me do it up over here. Okay, give me more space. So 1 minus 1/4. Here's a little bit of a review on how to subtract fractions. So In order to subtract fractions, y'all, let me go ahead and kind of remind you of, I think it's in algebra. I don't know when y'all learned about this, but you need something called a common denominator. Let me know if y'all remember that. So common denominator, that means this 1 right here, we need to make sure it's over 4. How do we do that? What we do is you put this 1 over 1. Just put 1 divided by 1. And then we have Janet there in the chat. Y'all can take a look at what she wrote in the chat. So I'm going to make the 1 have a divided by 1 right here. In order for me to have a common denominator, what I'm going to do is I'm going to multiply the top and bottom of this by 4 so that I can get a denominator of 4. I'm going to multiply top and bottom by 4. And again, Jeanette does have the explanation in the chat if y'all want to double check it, or if that makes more sense what Janet said. So we have 4 times 1 is 4. Divided by, and I have 4 times 1 is also 4. Then we're going to subtract by 1/4. Once we have a common denominator, everyone, you are able to subtract fractions. How subtracting fractions work is once your denominator is the same, you're just going to keep that. So the denominator is 4, keep it. The thing that gets subtracted is your numerators right here. So 4 minus 1. And that's going to get us 3/4. And that's how we got this right here. And if you were to use a calculator, what you would get is 0.75, which is equivalent. So if you did 1 minus 0.25, which is 1/4, you would get 0.75, which would be equivalent. So you could have also converted to decimals, and that's completely fine. So that is how we got 3/4. Let's see, does anyone have further questions about this one here? This is great to review this portion. Okay, so let me know if there's any additional questions. But if not, now we're almost there. Okay, Francisco, you already getting to the final answer? All right, so Francisco, what did you do to get that? What did you do to get square root of 3/2 for the answer? What do we do here? Like, I have a squared equals 3/4. What should I do next? Like, I have to get rid of that squared there. Oh, you use SOHCAHTOA. Oh, Francisco used SOHCAHTOA to find the other side. Oh, okay. Try to submit that for extra credit. And or if you show us a photo of it, I'd be happy to like also share with everyone else. So remember, y'all, I said there was 2 different ways to solve for the sides. One of them is SOHCAHTOA. Another way, which I'm showing you here, is Pythagorean theorem. You also can use SOHCAHTOA to find that other remaining side. Amazing. Okay, how about everyone else? How would we finish this? Like, I have a squared equals 3/4. What should I do? I need to get rid of the squared. There's something I need to do to both sides to get rid of that squared. Okay, we got square root, yes. We're gonna square root both sides, that's right. That's how you get rid of a squared, y'all. And I know there's like a bunch of algebra skills kind of coming back up here. Don't worry. We're not going to be recreating this. You just want to understand where the numbers are coming from is all. So don't worry if this is causing a bit of anxiety. Just follow along with us. Ask questions. Don't be afraid to ask questions. But this is what we do next. We square root both sides. Square rooting both sides basically helps you get rid of the squares. So this cancels out with this, and you're going to be left over with simply a equals, and then you have the square root of 3 over the square root of 4. That's going to simplify to the square root of 3/2. Now the reason for that, and I didn't have space on my side, is because this square root, you can break it up like so. You could break it up as square root of 3 divided by square root of 4. The square root of 4 is equal to 2. And that's why this simplifies to the square root of 3/2. That's how we get that simplified answer. And you can also use SOHCAHTOA to get that answer. Awesome. And I see 3 of y'all said square root. That is it. Whew, that was a workout. That was a complete workout, right? So we got that finally. We got the remaining side is a square root of 3 over 2. This side right here, the one we're like trying to figure out, finally, I'm going to put, we got that's a square root of 3 over 2. So again, once again, what did I do? I used SOHCAHTOA and I used Pythagorean theorem. You could have also just used SOHCAHTOA. Again, Francisco did that. Feel free to explore that. But now let's go ahead and try to make connections to this. Remember, you will not be asked to do this. I'm not going to ask you, hey, do SOHCAHTOA, Pythagorean, solve the triangle. We're not doing that because that was geometry. We're just trying to make connections to how this triangle here is related to how we're getting the coordinates on the unit circle. So again, do not be overwhelmed. You're not going to be asked to recreate this yourself. So don't worry about that because that's not the main juice here. Let me go ahead and clear my screen unless there's any burning questions before we go on to the next slide and then before we hit a Padlet. Okay, we got like 3 minutes left. Oh my goodness, this was quite a class. Time flies. Okay, let me go ahead and clear my drawing. So I guess I'm gonna have to prioritize what's important for us to get done right now. So let's see if we do have time for the Padlet. So give me a second. Okay, so here's our findings, everybody. So our findings are this, and I went ahead and I wrote this down. So we have that the sine of 30 degrees is going to be equal to 1/2. Why? So we know that sine is SO or SOHCAHTOA right here. So, and we know that this side was opposite and this side was hypotenuse. So if I was really to try to figure out what SOHCAHTOA was, I would say, well, sine of 30 is equal to opposite over hypotenuse, right? Well, my O is equal to 1/2, my opposite, and my hypotenuse was equal to 1. But remember, y'all, anything divided by 1 is just the number itself. So this is just going to be simply equal to 1/2. So sine of 30, everyone, is 1/2. That's where I got this part. The next thing that I'm going to do is the cosine of 30. So we know this is O, this is H, and this was A. This was A. So cosine of 30, we look at the SOHCAHTOA truths. Cosine of 30 is equal to, that's right here, A over H. So adjacent over hypotenuse. So that's adjacent over hypotenuse. So that's going to be the square root of 3 over 2 divided by 1, or simply just the square root of 3 over 2. Now, so it appears that in our next class, which is going to be tomorrow, because we're not going to have enough time. So in the next class, which is tomorrow, we're going to go ahead and take a look at this, and then we're going to do our Padlet. It was just such a very interactive class. I'd rather talk about the whys of stuff than to rush through what we're doing and why. So instead of the Padlet check today, let's go ahead and do our checkout right now. I want to know what made sense and what didn't about what I just did. So here's our checkout, everyone. And you can feel free to answer. I'm just typing it. Check out what made sense and what didn't on slide number 11. Slide number 11. Here's our checkout, y'all. It's in the chat, so don't worry about the slides there. Okay, Henry, we got everything made sense. All right. I am expecting like there's a lot, like there could be a lot of questions. This is like bringing up a lot of like math from geometry, right? So SOHCAHTOA, Pythagorean theorem. We got what made sense is understanding the Pythagorean theorem in SOHCAHTOA. Okay, that's great. We have it made sense. Is the homework like this? No, the homework is not like this. Like I said, you will not be asked to do this on your homework because guess what? This is geometry. We're actually more concerned about the patterns that we're seeing come up here and how it relates to the unit circle. So don't worry, but you do want to just understand where it's coming from. That's all. Just a little basic understanding of where these numbers, like 1/2, square root of 3/2, where are those coming from? That's all we want to know. We haven't made sense. It's a lot, but I understand. And I knew it was a lot. When I was creating this, I'm like, oh boy, this is quite a bit. And I knew it was going to feel like a workout. And then we says, do we have to use all the sine, cosine, tangent? We perhaps, I don't know if we'll have time to actually get through, all, not tangent. I don't think we'll get through tangent for the unit. I'm not sure. The end of the equation made the most sense. The beginning was the hardest to understand, but I got it. All right, that's awesome. Everything made sense. Sometimes what doesn't make sense is the formulas that go with what, right? Like knowing to use SOHCAHTOA, Pythagorean theorem. Yeah, that makes sense. I understand that. All right, we got SOHCAHTOA, Pythagorean theorem made sense. All right. What was the point to get A? That's a good question. The point to get A was to make sure we solve for all the sides of the triangle. I think it'll make sense why we needed to solve for all sides when you start to make a connection to how this triangle is related to the unit circle. All right. And a lot of you have made sense, Pythagorean theorem, SOHCAHTOA. Okay, so the processes in general are making sense. We do have a few questions. We're going to hold on to that. And again, we're going to continue our investigation tomorrow. Yeah, I appreciate y'all. Bye, everyone. Thank you. See you soon.
Bye, Mr. Donna.
Bye. Appreciate you all.